So I'm deciding I saw them earlier film time ago. Been a fan for a month. That's my new Ricardo, who just left, is an embodied cognition person. I had some really good conversations with him about his view on embodied cognition. And he said that some things we have to accept that logically. Like affiliation is not part of a Western thought, logical decision making. And that's sort of what this process is really. So I'm trying to compensate the energy of other affiliations.
My work has a chance.
Yeah. So what kind of job is now?
He's applying for a fellowship, so he's through residency now, but to do a fellowship is a whole other match process.
I know about that.
Oh, you do?
Yeah. My brother.
So you know how intense it is. And so most of the fellowship interviews we've gotten so far have been all over. And so this was the first one in San Diego, and I was like, by the way,
Fellowship in what?
sports medicine.
Oh, okay.
That's a really good program.
Yeah.
And they turned out like they didn't offer him an interview because they didn't see his application. And so he sent another email. I kept pestering. I was like, just send him an email. Just like ask him why you haven't gotten an interview yet. And they were like, oh, we never saw your application. Let's go back and check. And then he got less than 24 hours later. He got an interview.
Well, packets too.
Oh, okay. We'll share.
You want to give me a couple of back here?
I've been spending all day revamping labs. I inherited these labs from a previous professor, and they're all out of whack. Like, they don't make any logical sense. And I am pulling out my hair in mineralogy, study of minerals.
Important.
Well, now we're moving into the microscope. So
Easy to go over here. Easy to go over here.
I need a pair. Yeah, I'm excited.
Does anyone need a packet?
How about 3 times? If you hear me, clap 3 times. Okay, great. Welcome back, everybody. Good afternoon, and thank you all for coming. It's really wonderful to see you. My name is Bill Zahner. I am a professor in the math department, and I teach math education courses. I've taught some of you, not all of you. So it's good to see some familiar faces. I am delighted to introduce our speaker today, Judit Moschkovich, who is coming from UC Santa Cruz. And Dr. Moschkovich is a renowned expert in the area of language and literacy and mathematics education, and also an accomplished researcher in mathematics education in the area of student learning of algebra. Dr. Moschkovich was the PI of the principal investigator of a National Science Foundation funded grant, whose name escapes me right now. Well, not that one.
Oh.
Prior to that.
Something about mathematical discourse.
Mathematical discourse, when she was at Turk in Boston, actually in Cambridge, Massachusetts. Then she went to UC Santa Cruz, where she was the PI of CEMELA, the Center for the Mathematics Education of Latinos and Latinas. And that's a center that is near and dear to my heart because they paid for my graduate school, so thank you for that. And Dr. Moschkovich is presenting today on academic literacy in mathematics for adolescent English language learners. And I'll let her talk more about that, but we are just delighted to have you here. And before we get too far along, I want to say thank you to Meredith and to Donna for letting us crash your courses. And I hope that this is a great opportunity for everyone. So thank you, Judit.
I'm happy to be here, and I want to have a little bit of a sense of who you all are. So raise your hand if you're going to be teaching math. Okay. Raise your hand if you're going to be teaching middle or high school math. And raise your hand if you're going to be teaching science. Okay. And raise your hand if you're going to be teaching something other than math or science. That's okay.
I'm doing science and computer science.
Cool, that counts. Okay. And I know there are people interested in literacy. So I'll tell you a little secret about myself. I'm in math education, but it turns out that several of us, I'm not the only one, I found out, I didn't study mathematics, I studied physics. And ever since I started to do both research on math education, I work at the sort of the boundary between mathematics and physics. The problem we'll work on today is a distance rate problem, and that's one of the places where we start introducing students to how to use mathematics to think about motion. So don't feel bad because you're in science. I don't. I think that coming at mathematics through physics was really important for me. I also did a little tiny bit of biology when I was at Turk, and it was great because I felt like a total beginner. But I do understand biology much better having done that. So what I'll talk about today is the latest way that I've been thinking about the question of how to integrate language into how we think about learning and teaching mathematics. And I've been at this for a while, and I think I finally, and I do mean a while, I finally have it sort of coherently together, the different parts of the pieces of how we talk about learning mathematics and language in mathematics. So I also was hanging out with people who work in literacy. And from them, I really got the point that we're not just interested in language, we're interested in literacy, and I'll tell you why that's important. What I'm going to do today is describe how academic literacy in math, and if I got tired of typing it, so it'll be ALM, is more than competence in using words and numbers. I'll illustrate three components of academic literacy in math. Math proficiency, which you should be familiar with, they have 5 strands, practices, and discourse. I'll illustrate how academic literacy in math involves multiple meanings for words, multiple modes, and multiple resources. Sometimes those of us who come from math or physics tend to think that words and the meaning for words come out of our mouths into other people's minds and that they're copies. And that's a challenge for teaching and for learning because that's not how human beings work. So this is a challenge again for working in classrooms with kids who are native English speakers as well as kids who are learning English. And if I get to it, we can talk about what do classroom environments look like that support academic literacy in mathematics. And hopefully I'll leave some time for questions at the end. I've set my alarm if it lets me for 5 o'clock because I'd like to, in about 30 minutes, get to do the videotape that illustrates these ideas and lets you do some looking at the videotape and working in pairs on the videotape. If there's anything you don't catch, all of this comes from these 3 publications, and we'll post this somewhere so you can have access to them. You don't have to copy them now. So again, the shift is from academic language, which you've heard that phrase, to academic literacy, or academic English to academic literacy. It's important for all students that are developing literacy, academic language, mathematical discourse, and so on. Those kids who are learning to be better readers as well. However, it's essential for English learners and bilingual students. What's new in this definition is that there's some framing assumptions for academic literacy. First of all, math activity, some people think, oh, I do math by myself, I don't use language, I just calculate. assumption is that it actually involves language, representations, and social interaction. Not all of them all the time, but if you're reading a textbook, you're interacting with somebody who wrote it. Even though there isn't a human being there, you're still interacting with the person who wrote that. So social interaction doesn't have to be with an actual person there, but it's more with a community of people represented in that textbook. The focus is on the potential for progress. I'm not interested in looking at misconceptions or deficiencies. I take this from a Vygotskian framework, if you've heard that before. It's a really important piece of a Vygotskian framework that sometimes we forget. And what I want to do is expand academic literacy so it goes beyond simple views of language as words or vocabulary and mathematics as number or computation. If you ask people out, on an airplane or out at the supermarket, when you say mathematics, they really think arithmetic, right? Some of the implications is that discourse, and I'll talk more about what that means, is central, and that the meanings for words aren't given but constructed by students as they do mathematics. So let me start by one of our favorite algebra word problems. And what I want you to think about, not like, oh, how horrible these were, and just let's read it together, but think about where's the academic literacy in mathematics when you try to grapple with this word problem. A boat in a river with a current of 3 miles per hour can travel 16 miles downstream in the same amount of time. It can go 10 miles upstream. Find the speed of the boat in still water. I'm going to take a deep breath and a moment of quiet to observe this. First of all, notice how long the sentences are, how complex they are. Yes, this is how middle and high school word problems are written. And we can't change that. That's a genre. They've been written this way for a very long time. But we can help students learn to read them better. I always wanted to know, how do you measure the speed of the boat in still water? Do you stop at the river? So I always went down the wrong direction. But it is important that when students are reading these, you're not trying to make sense of a story. This is a word problem. You have to just pick out what you need to think about, how to relate the quantities. And you have to learn to read that way. So that's why I went to physics, because I wanted to know, how do you measure the speed of a boat in still water? So what academic literacy in math is not, is first you read and understand the words, and then you use keywords to write an equation. We know that leads you down bad paths. Things that you do that don't make any sense to you and don't make sense in terms of the word problem. So this is what it's not. We'll start with that. It's not extracting the correct numbers or quantities or variables and relating them with the correct arithmetic operation or writing the correct equation. So let's see what it is instead. I'm proposing that we need at least 3 components. And for me, because I went off in the direction of studying mathematical discourse and mathematical practices, and I'll tell you what those are, I felt like I had left behind this wonderful way that we have of thinking about mathematical proficiency. And if we do that for English learners, we're doing them a disservice. Because what typically happens, in remedial classes particularly, is that all they will be doing is procedural fluency. If we have the 5 strands, that's the one that they're going to do over and over and over. So it's important to remember that math proficiency has more than 1 strand. So I couldn't find the perfect image, and you're only going to see one picture in my slides. This was the one. I wanted to give you a sense that these 3 are organically connected. They grow together, they work together. They're not separate. They're not like the strands. They're actually like bamboo growing. Math proficiency, math practices, and math discourse, that's what makes this a complex view of mathematics and language. Things are not separate. And I'm assuming that mathematical thinking and learning involve language. So here's just a review of what Kilpatrick and Swafford and Fendel in 2001 set up as 5 strands. I'm always very, very interested in conceptual understanding, a little bit less interested in procedural fluency, although it allows you to lead into understanding. Adaptive reasoning, I tend to just call it reasoning. The parts in blue is I always take things that other people give me and then change them to my own words. we were interested in understanding, representing, and reasoning. So we know there's 5 strands, they're all important, but the really important pieces are those 3. I usually do a little example, just so we're all on the same page, and I did not make this up, I borrowed it from Wertheimer, who was doing this in the 1940s, so this isn't mine. He actually went and looked at kids in a, I forgot, it was a secondary classroom, and he didn't use this exact problem, but when I try to make it a little simpler, he said if a student took that problem and added it up and then divided by 5, I would say they have procedural fluency. What Wertheimer said is if instead, he just said, oh, well, the answer is 13 because I know that repeated addition, they won't say it in exactly those words, repeated addition is like multiplication and multiple division undoes multiplication. I would call that conceptual understanding. Now, they're not going to know that the concepts they just used are, one is the repeated addition model for multiplication, or this other even more beautiful one. And you know, in math, we're interested in elegance. And there's nothing as elegant as inverse operations. They undo each other. How does that happen? They're not going to use those labels, but when teachers ask me, so how do I teach for conceptual understanding? And what's a concept anyway? How would I recognize a concept if it walked down the street and waved at me? Probably not. But we do know that in certain situations we can say this requires understanding some concepts. But the students don't have to know the words for those concepts. They don't need to actually tell you, I did this because repeated addition, I did this because of an inverse operation. They will tell you in their own everyday ways of describing that and in their own children or adolescent ways. Let's see, how many of these can I? No, let me skip over these. We have more examples as we get into more middle school and high school examples. So if you can multiply half by a third, we would call that procedural fluency. If you can explain how you reach the answer and why you take each step, and more importantly, why the result is smaller than the number you started with, and if you can draw what it means. I've started to think that conceptual understanding is really about the meaning of what you're doing mathematically. So after a while, you know, after 20 years or so, it's been more than 20 years since 2001, we say conceptual understanding. What do we mean by that? I think I'm going to focus on, do you know what it means to multiply a half by a third? And I work with math majors who sometimes have to stop and say, oh, I'm not sure I know what that means or how to explain to you what that means. Certainly, division by fractions when you're a math major takes us 3 weeks to go through developing some meaning for that. And then I'll skip over that. So, again, this is partly what other people have said, but I'm focusing on meaning, reasoning, and connections. And you can ask students certain questions to, well, it's hard to say, what does that number mean? They might look at you like you're a little crazy, but you can work in a classroom where students get used to the idea that what they're doing needs to make sense to them and mean something. Reasoning, why is this the right answer? And then our favorite, NCTM has been at this for a very long time, connecting representations. So that's the first component. The second component is mathematical practices. So years ago, people started, actually I found that Alan Schoenfeld mentioned mathematical practices back in 1992. But I asked him, I said, well, you know, I wasn't really sure what they were at that time, and we started to look at those. I'm going to use 3 sources for thinking about these. My own work, the NCTM standards, and the Common Core has picked up on some of the research on mathematical practices. Basically using language and other symbols to think, talk, and participate in the practices that are the objective of school learning. I want you to think about, though, that the practices vary across communities. We don't want all kids to be mathematicians. Well, maybe we want them to be statisticians. So there's different communities, and what happens in different communities will involve different practices. There might be a traditional classroom where all of it they're doing is procedural, and they're working on worksheets. And then in other classrooms, they might be justifying and reasoning and sharing their thinking more. However, even given all that variation, there are common practices that we would label as academic mathematical practices. And then I'll use a definition by my colleagues. Taken as shared ways of reasoning, arguing, and symbolizing established while discussing particular math ideas. So they're specific to particular math ideas. So the NCTM standards didn't call them practices, but they're there. They're the same kind of thing, phenomenon. Problem solving, sense making, reasoning, modeling, looking for pattern, structure, or regularity. I think this is really important because we've gone from thinking, if you ask students, what patterns do you see? They don't always see the patterns that are mathematically important. So we say, well, we're looking for structure. What we're interested in is the mathematical structure. And we're obsessed by regularity in mathematics. That's really, another way to call these habits of mind. People, Mark Driscoll has 2 great books on algebraic thinking and geometric thinking, and they call them habits of mind. For example, generalizing, abstracting from computation, more general ones, mathematizing. So I keep my own list. It's an amalgam of all of those. There are, let's see, what am I missing from that list? Oh, yes. My favorite one that we tend to forget is imagining, because so many of the things that we do in math aren't in front of us. Straight lines, there isn't a straight line in the world. There's just segments. We talk about them all the time. We love to do that. Infinity, we can't go there, we can't see it, but we know we're talking about it. Zero, zero's tough. Absence of something, absence of everything. So imagining, I would also consider mathematical practice. And then there's the Common Core standards for mathematical practice. We have 8 of them. I'm going to give you, again, how I make sense of these. I don't think that one should be there. It's too vague. I don't know what tools they want us to, so I just threw it away. Making sense, reasoning, arguments, modeling, precision, structure, and regularity. They have to have full sentences, but that's how I remember them. Otherwise, it's too much. I can't remember more than 3 words at a time. And sometimes I forget the 3rd one. So. This is how I organized it for myself. And not only because there are science people here, but because it's important that we connect mathematics to science. Again, how many of the kids in our classroom are actually going to just be doing math? They're probably going to be applying math to something. And it's not only going to be physical science, it might be social science, it could be. So, here are the 8 practices from, I just call it NGSS. Next generation. I know there was a Star Trek reference there. Next generation Star Trek. No, next generation science standards. The 8 practices. I would say that where there is an overlap is in this last one. Analyzing and interpreting data, there's no better way than doing that than with math. Because it gets so clear, so regular, so structured. That's what math does for data. Using mathematics, constructing explanations, argument again, and then obtaining, evaluating, and communicating information. The 3rd component is mathematical discourse. And I'm going to use a quote from Betsy Brenner, who's at UC Santa Barbara. Many of those mathematical practices involve mathematical discourse. As students develop academic literacy in mathematics, they're learning to communicate mathematically by making conjectures, presenting explanations, constructing arguments that involve mathematical objects with mathematical content and towards a mathematical point. I actually think only half of the quote was hers. I just realized that. Sometimes, I say that other people said things when I said them. So why mathematical discourse? Why am I changing from language to discourse? The word language means too many different things, and we have intuitions about language as human beings. We tend to think that language is one thing. It's what comes out of our mouths. It's static. We tend to think that we learn language by learning vocabulary, even though If you've ever learned a second language, you know how little vocabulary helps you when you want to learn. So by switching to a different word, we're trying to refer to something else that isn't just our intuition of what language is. And because we've learned from research that the simple meaning of language is single words, vocabulary, or the proper use of grammar is not what students need in order to be able to do that. This shift is essential for English learners. Why is that? Because if we overemphasize correct vocabulary and formal language, imagining that our job is to get students to talk like math teachers or mathematicians, then we're limiting the resources they get to use to make sense, to learn, and to understand mathematics. It also precludes students from participating in those valued mathematical practices. Students, actually human beings, are not going to come out speaking perfectly whenever they're learning something. In fact, when we ask students to present, they're going to give you a polished version of what they did when they were working in groups. Much more of the mathematical work is going on when they're working in groups, and it's going to be less polished. So again, mathematical work goes on in those settings much more than in the presentations. I did a paper a long time ago showing how students were modeling a station in Antarctica and using functions and scaling to model that station. And they did wonderful math things with scale and with functions in the small groups. When they came to the presentations, they were mostly interested in looking good. They would argue, yes, but it was to win the argument rather than to talk about the mathematics. Which makes sense if you're presenting your design for a station in Antarctica. Great, I beat my own clock. So the points I wanted to make about math discourse is that it involves multiple modes. We, again, not just talking, but talking, listening, reading, writing, drawing, graphing. That's the modes that I'm referring to. And that the meanings for words are not static, but they're negotiated. We use the word situated. They're also dynamic. And that students are using multiple resources, both everyday and informal. And the formal word for what I'm talking about is called a register. There's a lot of confusion about what a register is. I started out very early on in my career thinking I understood what a register is. It's not a list of technical terms. It's different ways of talking. And the best examples of what a register is are legalese and baby talk. You think, and I still can't do imitations of those, but when you go to talk to a lawyer, and they're like going on and on, it's the words, but it's also the fact that he's wearing a suit, that you're in an office, that there's certain things that you talk about, certain things that you don't. And then baby talk, I'm talking to animals. It's great. You know, that's just a totally different way of relating to the babies than you do with adults. So it isn't only vocabulary. That's the important part. Okay. This is good. Now I know I'm skipping to the example. Good. So what I would like to do is share an example with you using the lens of those three components for academic literacy. What I'm going to ask you to do is watch a video clip. I'll tell you something about it so that you don't have to wonder and guess where it came from, who the kids are, and what's going on. And then I'm going to ask you to look for those three components of academic literacy in math. And that's what I want you to spend most of the time doing. So let's see. This is a research project. This is how I do all my work. I do both short and long-term ethnographic observations, videotape whole class and small groups for selected lessons. And then I ask students to go and work in pairs, calling those peer discussion sessions. And they're going to be discussing a graph of motion because that was the lesson that I observed. This was a school that was K through 8 in a large city. From grades K through 6, students were immersed in a Spanish-English bilingual program. And then in this classroom, which was grade 8, they could decide what language they wanted to speak. 60% were eligible for free or reduced lunch. They were using the Connected Mathematics Project. Raise your hand if you've seen Connected Mathematics Project. If you haven't, it's really good. And it still works. They were looking at stories of bicycle and walking trips. The teacher was Spanish proficient. She used Spanish and English flexibly. She was part of a seminar on discourse in math and science language minority classrooms. There were students in this classroom that went all the way from being, well, they were all bilingual because they'd been in the bilingual program, but there were students who were Spanish dominant and had arrived maybe 2 years ago, to students who were not immigrants from a Spanish-speaking country and were still bilingual because they've been in the program. The students that you're going to see are actually in the middle. They're bilingual, they're native Spanish speakers, they're proficient in both Spanish and English. They do belong to a bilingual community and they've been in that program for several years. Everything you'll hear is going to be going on in English. I picked that because most teachers and most people only understand English, and I'd like that to be part of what you get to understand. And also, most teachers need to manage students speaking in English. So let's see now. If you can go to the handout, I'll just walk you through what's on the handout. And you should be sharing, but we don't have enough for everybody. The problem is on page 2, and I'll do what we might do in a classroom we did out loud. But I need to tell you something more about it. They took this problem for homework, worked on it, and brought their graphs in. So, on the second day of their bicycle trip, the group left Atlantic City and rode 5 hours south to Cape May, New Jersey. This time, Sydney and Sarah rode in the van. From Cape May, they took a ferry across the Delaware Bay to Lewes, Delaware. Sarah recorded the following data about the distance traveled until they reached the ferry. So on the left, you have the time in half-hour increments, and on the right, you have the distance in miles. Now, there's lots of interesting conversations that students had about the table. That's another paper that I'm still writing. But what I'd like you to look at is just the first part of what they did, which is to make a coordinate graph given the table. And you've got the graph that Carlos made and the graph that David made on the next page. So I think what I'd like you to do is just take a few minutes to make sense of the graph. You can talk to the person next to you.
Axes are totally different.
And I'm going to go get the video while you do that.
Axes?
Oh, the axes.
Yeah. So these all are correct, but they look different because the axes are scaled differently.
Yeah, I'm trying to get a handle on how to scale this
Looks like
But on the x-axis, it takes 2 axes to equal it.
Yeah.
So it's making this much broader. But if you were to get a rate, if you were to do distance over time, you'd still get the same answer.
Yeah. So how it might, again, how it or if people can feel things from the charts, or if they, feel I've had students who sit something to work. Like I teach these kinds of courses tasks that you engage students in that. The graph itself, what you tell where you are.
I would never even think of this. Right. Right. Because they don't look the same.
Yeah, because this is a different thing. And they're not any, you know, that's, myself, like,
Yeah,
it's not true.
that makes it easier for me to comprehend. Whereas here, I mean, every half step it goes up by 2. So there's still that one, but it's harder to see them. We're more important than 10. They're like that's probably also why it looks aesthetically nice.
No doubt.
Because of the power.
Different. Yeah, that's
Exactly.
There's all kinds of
What do you think about this?
stories around.
I like the fact that they put distance and time. I don't know what's the axis are.
Exactly.
Yeah.
Who do you trust? Your authority.
Grading my midterms this week, my students came up with answers that have no factual basis. Like, I don't even know where they learned some of the things that came up. Like, we never talked about it.
I just don't think it's that big.
Oh, yeah. And you've never seen anything like it before?
But I mean, like I think about it, there was something in it that was really bugging me. And I couldn't encode it. You know, and I was like, I need to just, you know, I'm doing this, and there's water. I mean, there's a natural ones, and I'm like, this far. Yeah, and like there's a big in it. Stop wondering about rotation. There's nothing about this test is about that.
Yeah. It's in the back of your brain, yeah. Well, I wonder if any of that was going on in my
So, before we look at the video, I always have to think about the problem and think a little bit about what the students did. I'm going to ask you to do one more thing before we look at the video, which is to think about the task itself, because you can use that framework of looking at academic literacy and math to think about the task. So, what academic literacy in math does the task require? Well, first of all, multiple representations, right? That's literacy also. Reading a graph is literacy as well. Connecting the text table and the graph. Again, mathematical proficiency, connecting representations is typical for a task that involves conceptual understanding. We've been using those for a long, long time. What are the mathematical practices just when we look at the task? Would be modeling with math and making sense of the 3 symbol systems. Now, if we think about what other mathematical practices might be present, it will depend on what we call the activity structure for the problem. How the teacher organizes for the students. I'll tell you what this teacher did. She asked them to discuss the responses in small groups, to arrive at joint group solutions, and then to present the group solution to the class. Without that activity structure, this task wouldn't engage students in I have these memorized. Math practice 3, which is constructing viable arguments. The second part is critiquing the reasoning of others. So again, the math practices are not inherent to a task. They depend on how you organize the task in a classroom. We call that the activity structure that the teacher provides in the classroom. So what I'm going to ask you to do, and again, you can look at videos for lots and lots of things. But what I want you to do is look at 3 things. How do you see math proficiency, math practices, and math discourse? And you might want to write that down because I won't be able to keep it. Did I put that on the handouts? No, just write that down. That's what the 3: math proficiency, math practices, and math discourse. I also want you to focus on what resources, modes, and representations students are using, so that you can see the complexity of literacy in mathematics.
Like a procedure?
And you will not be able to understand this clip unless you think about what are the meanings of words and phrases for what's going on. You'll see in a minute why that's important. So you don't have to copy all the words, but make sure you have some sense of, you're looking at math proficiency, practices, and discourses. Too bad discourses and start with a P. And then resources, modes, and representations. And then the last one, what are the meanings for words and phrases? And now I'm going to go get the video clip. So everybody, do you need more time to get those? So the question that David will start with is, here's my graph. Did it come out like yours?
Did it come out like yours? I don't mind.
Because you did it upwards.
Oh, you did?
Were we supposed to do the graph upwards or
Crooked and then
or horizontal?
doesn't matter.
Because like when we look at our graphs, it's going up and mine's going to the side.
Did you have the same, did you both put the same things on the x-axis and on the y-axis?
No. Yes.
You both put time here. Okay, so what's different about these? I don't think it's the positioning of them. Look at your numbers and where you placed your numbers.
Oh, that's true. Because that one by 2. Oh, 1, 2.
You skipped
One by
one.
one.
So how did that change how it looks?
Because it doesn't go up as far. It only goes. It's more steeper. It's more steeper.
Similar to the difference between this one and this one here.
Yeah.
Right? Here the numbers are closer together, so it looks steeper. Other than that, are they the same graph?
No, also the other.
This time.
X-axis.
I went by 2.
This is the x-axis.
This is the y-axis. This is the x-axis.
I went by 2.
You went by 2s and you went by...
I went by 2s. You went by 1s.
No, here, on the y-axis.
Oh, I went by 5s.
You went by 5s. No, actually, you didn't go by 5s. You actually went by 2.5s. Because you did every 2 spaces was 5.
Then you only went by 1.
Every 1 space was 2. Yes. You'd see they're almost the same. If you look at the next
Wait,
one.
but I don't get what you're saying. Because
Okay.
I went by 5s.
Okay, your numbers, right, the numbers you have are by 5. Okay. If you look at one line here, what number is he at?
2.
What number would you be at if you had a number here?
3.
Almost 2.5,
Yeah.
because I'm halfway to 5. Okay? At this point, after 1, 2, 3, he's got 6. For you, after 3, 1, 2, 3, you'd be at 7.5. You see what I mean? So it's actually at 2.5. The numbers you wrote are by 5s, but since you skipped a line in between, each line is 2.5.
Okay, take a deep breath. Sometimes this reminds me of who's on first. This happens in math and science classrooms. We think we're talking about the same thing, and then it turns out that maybe we're not. So what I'm going to help you with, just because of the time, I usually, raise your hand if you'd like to see the video again. You could also do that. Okay, not enough people. Okay, I'd just like to check that out. Because seeing a video just once gives you, and I did want to say that Stefan was the young man who wasn't talking. That wasn't the way it was always for him. This was a bad day, he wasn't feeling well. And so his buddies actually kind of, left him alone that day. So don't, that's the first place people are, oh, what happened to the third kid? Why wasn't he involved? Okay, so you have the transcript. I would like you to look at math proficiency, math practices, math discourse, multiple representations, and multiple meanings. And we'll give you for sure about at least 5 minutes to think about this.
Same thing, represent the same thing. Theirs was just right.
I don't understand the definition of these things, so I've never worked with this. But I think it's interesting that when she finally corrects him and he thinks he gets it, then he looks at his partners and he says, oh, but you only went by 1. And so he then confuses the interval with the number of segments.
He will remember every box. Is that what you mean?
No.
I was wondering if they had
I'm specifically referring to his comment that I underlined, and he only went by 1.
Where do you think the 1 is?
Right here.
I mean, over a box.
Right. So he's confusing what it is. Yeah. Or tick mark.
Tick mark,
Yeah.
That's fascinating. I really see this a lot. The village should be represented.
Yeah, tick mark.
But then the you know, it might be where do you think?
Yeah.
She brings in the art for her art. What we did yesterday. So her role is to read information. And this is cool. So I wonder if there's something going on with the correctly to read what I asked.
So like to get to 5, you have to leave 5 tick marks.
No, not even that. Here's that makes it hard. They're just stopped.
Oh, I see. That's how you define.
That's how you do it. Not that that's up, but I just, I think.
Lots to notice and lots of things to wonder about. I did want to mention that this is a very experienced teacher. And even though she was an experienced teacher and she was in a seminar where we were talking about how to have great classroom conversations, she had to struggle with what's going on here. And she did really well. Again, this is on her feet. She continued this later on, so don't think that this just stops here. This theme of what happens with the scales went on once she figured out that this was something that kids needed to think about. So, first of all, what did I want? Oh, yes.
Yeah.
We can all agree that they were using different meanings for the phrase I went. I want you to know this is not the only classroom or the only group in this classroom where we've seen this. I don't have, lots of quantitative data about this particular phrase, but kids and teachers will use this to describe units or unitizing. So here are 3 different ways that I think we're going on here. One way of saying I went by 5s is the value of the interval between labeled tick marks. And I had to find some way to talk about this. So if that makes sense to you, there's the pictures extracted. So when Gabriel says I went by 5s, he's referring to that. And David says I went by 2, and he's referring to this. The second way is to use I went by to refer to the number of segments between labeled tick marks. So Gabriel says I went by 2s, and he's referring again to his own graph. And he says, but wait, he went by 1. And sometimes he says 1, and sometimes he says 1. 1 would be, the teacher says no. Actually, you didn't go by 5s, you actually went by 2.5. She means something different. And I believe what she's thinking and has in mind is a concept of unit and unitizing, which is what she, again, imagines will get them out of their trouble here. David says, I went by 2s. Because that you did every 2 spaces was 5. So, mathematical practices. But let's go back to the multiple meanings. What I want to say first is that we cannot avoid multiple meanings by giving students a vocabulary list with definitions at the beginning of an activity. This came out of actually doing the activity and having their own meanings and constructing them. So it's not that, oh my goodness, the teacher wasn't good. She didn't tell them what I went by means. First of all, I went by is not even formal mathematical way of talking, right? It's coming from the kids, but it's actually in the classroom, and it makes sense to them. But they need to negotiate what that means. Even if you used unit or scale, students are going to have different meanings for those words, and they'll still have to negotiate what they mean. And they will do that during their work on a mathematical problem, no matter how much you give them a definition at the beginning, because in fact that's what linguists tell me is the nature of language. It's much easier to learn a second language if you, for example, go to Mexico and need to learn how to take photographs. You will learn the language of doing photography as you're taking the photographs, not by reviewing a list of technical words about photography. Now, moving on to mathematical practices. Does everybody agree that they were constructing and critiquing an argument? Certainly critiquing. And imagine what kind of classroom this is that this can go on like this about that small piece. Again, students are expected to critique each other's arguments. And by the way, the argument is important because the steepness of a line is impacted by what you do with the scales. You can lie with the scales, as we know. So this is an important concept going on here, and they need to sort this out. Now, this is where I think when we look at attending to precision, again, is partly what I've been talking about. I do think they're attending to precision, but it isn't about a particular word. It's not about whether they said I went by or used the word scale or unit. They're talking about the precision of a claim that they're making. So how can I decide whether you went by 5 or you went by 2 unless I know precisely what you mean by that? That's a mathematical attending to precision. And I would not want people, particularly who work with English learners, to think that precision is about only letting kids speak when they're using exactly the precise, beautiful mathematical word. Because that would be detrimental to kids. They wouldn't be able to communicate and negotiate needs. So, whether you went by 2s, by 5s, or by 1s depends on what you mean by that phrase. The fact that it's a everyday phrase is important and it's a resource. And the meaning of the phrase, what went by, depends on how you're viewing the scales. Those two are connected. It's not just the meaning over here, it's connected to your perspective on those scales. And lastly, they're doing something that we get very excited about when you're connecting a claim to a mathematical representation. If you think about most theorems, there's some representation going on there. You're not just making an argument, but there's a representation that you're connecting your claim to. And then, of course, they're imagining. The teacher had to actually help them imagine a different unit. They're talking about an imagined object, a unit that's used to measure but need not be marked on the graph, and visualizing the imaginary relationship between marks and units. So notice in the example again that academic literacy in mathematics involves situated and negotiated meanings for words. They were both multiple modes in that they were talking, listening, reading, graphing, and multiple registers of ways of talking, both everyday and academic. What else did I want to say? Whoops, I went back, sorry. Yes, notice that white by is not a technical phrase, but an everyday phrase with a mathematical meaning. So both of the registers are resources, and what makes the discussion mathematical isn't because it involved a mathematical term, but because it involved mathematical concepts and the mathematical practices that I just listed for you. What are the math ideas in this discussion? And people have seen different ones. Definitely something's going on here about unitizing, the role of the y-axis on the shape of the graph, and slope. Now it turns out that other things happen in this class. If you're worried about Carlos, in one of the articles I wrote, he shows up 2 months later. The teacher is trying to help other students see the impact of the scale on the shape of the graph, and she calls on Carlos, and he proceeds to do an explanation that is really quite brilliant and clear. So if you were wondering, I don't want to leave him just going on, okay, fine, whatever you say, teacher. Again, there's no cause and effect here. It was all going on with lots of other things going on in the classroom, but we do have him on videotape having a different perspective on the impact of the scale on the slope. Now I start to repeat myself. In summary, what I'm suggesting is that this view of academic literacy for mathematics shifts us away from thinking about language as vocabulary or textbook definitions. We shift away from single views of math discourse as only what mathematicians do. And also that we stop thinking of everyday and academic as opposing. Actually, Vygotsky said that these work together. And you might start thinking for yourself now many times when you're doing mathematics or doing science, how you mix the two up. Things are not pure academic or pure everyday. I want to leave time for questions. Again, for teachers, what do you need to know and do? Provide opportunities for the 3 components. Make sure that you're paying attention to the cognitive part, reasoning, thinking, conceptual understanding, metacognition, but don't forget mathematical practices and discourse as well. And remember to create participation structures and norms that support those math practices and discourse. And use a complex view of math discourse where particularly meanings are negotiated and situated. And I think I'm just going to move forward to questions. I knew I did that in a Yes.
I have an eager question. I really appreciate this talk and the framing, but what I'm really thinking about is the very thing you crossed out on your list of math practices, but the strategic use of tools. So I'm thinking about everyday tools and academic tools, like a graph or a y-axis seems very academic, and say maybe a ruler that is around my house or I've seen it, that seems that maybe could be an everyday object. And I'm thinking about how rulers, when you mark the units, you always leave space for the other tick marks. And I just wonder if Carlos has a lot of rulers.
This is great, because there's no reason I should be taking that off, right? I just happen to not like, I shouldn't be on tape saying that I don't like math practice. It's probably really important, and particularly for those reasons, and also because Vygotsky really was obsessed with tools. So yes, and I'm going to think about, academic and everyday tools and how a ruler can be a little bit of each.
Right.
Right?
And well,
It
that's,
has its own tick marks.
yes. So one might think that you should label correctly. You should label your axis like a ruler.
Yeah. Yes.
I actually kind of expanding a little bit. Not too long ago, I was teaching middle school 8th graders how to use a graduated cylinder. And one of the things we actually were focusing on was some graduated cylinders have different physical scales, and you have to pay attention to that. So I was noticing, so when it comes to tying the physical science to math, the tools and the instruments we use all have different scales or different readings, and it's important in math to recognize that when you're trying to represent anything.
So there is science in here, right?
Yeah.
Anybody else?
So I mean, I think one clear takeaway from your talk is like giving students the space to engage with these problems, negotiate the meetings, that sort of stuff. But what about, like, as a teacher, what scaffolding or supports might you use in your classroom with types of representations or other things like that? What can you do to help the students grapple better?
So a couple of things. One is that in one of the pieces that I wrote, I was forced, I want to say forced by the editor of a journal to analyze what the teacher was doing that I thought was positive, not to criticize the teacher. And the way I framed it was something called an instructional conversation. Because, again, by the analysis that I did, she kept going back to something the students produced and then going with that. Now, other people could do other analyses, particularly if you study teaching. I don't analyze and study teaching as much, so this is why I had to be forced to do that. In terms of scaffolding, I just recently wrote a piece about scaffolding language. One of our favorite ways let me back up. One of our favorite teacher talk moves, if you've heard it, is revoicing. Taking something a student says and recasting it in a more mathematically formal mathematical way of speaking. And I have several examples. I think it would be both here and in another piece that I wrote. It turns out that you don't need to tell students directly. Well, okay, we could argue about, and researchers do because we love to do this. Do you need to tell students directly? I am now going to be using the mathematically formal word, so please use that in the future. I'm on the side of linguistics that argues that we learn language by hanging out with people who are experts, and then we start talking like them. So if the teacher simply recasts, that's good enough. But again, we could get into these academic arguments about whether you need to teach formal discourse explicitly. Probably is going to be a little bit of each, that sometimes if kids are not aware that we talk differently in math class, you might want to stop and say, have you ever stopped to think about the phrase, is this true for any number? It doesn't mean what it means at home, because is it true for any number in math class means, is this true for all numbers? But we just do that as if, so that's just one example. Right? Other examples are the word function, set, things like that. So revoicing is it's a language way to scaffold. Another way to scaffold reading, which we've thought about a lot, I want to show you some resources. If you go to ell.stanford.edu, there's a project called Understanding Language. We wanted to help teachers have activities for helping students learn to read word problems, because they do need help with that. So on this website, and I'm going to go, where am I going to go for that? No, that's not it. I'll just leave it there. Yes, we have to go online. So there are actually what we called language of mathematics activities, and there's one of them that helps you support students in learning to read word problems. What I can do is, instead of wasting your time going online, is send you that URL. The other activity that we designed, actually we borrowed it from Rafaela Santa Cruz, who is here. It's mathematically speaking. And again, she has a great activity. You can use it in all grades, math and science, where you first work on an activity. After you've worked on the activity, you set it up so that two students talk to each other. You do give them a list of words that they need to use, but they need to use them to do something after they've worked on doing something with beakers and looking for an interesting thing in science or working with an interesting math problem. So mathematically speaking, that's one activity here, and they're hard to find, but I can send them to somebody here so that you can take them, use them, and change them. The last tool I'll mention is actually available online from Balanced Assessment. It's called the Mathematics Argumentation Tool. A bunch of us from Understanding Language got together and said, so how do I help students create a mathematical argument? Because they're certainly not coming into the classroom knowing how to do that. And I can't just assess them and say, oh my God, none of them know how to do this, because we know they don't know how to do it. So we are working on making the tool better. It's very, very drafty, but please, again, I'll send it to people here and try it out. Think about, we're not thinking of stages, but where are students starting? Formative assessment, where are they starting? And where would you like them to get to without expecting them to jump to being great argument makers? There must be something in between that we do to scaffold them. So yes, there are tools for helping teachers help students get better at both math practices and mathematical arguments.
We're out of time, so I just want to thank Judit one last time for coming. Meredith and Donna are somewhere and they can hear me, so their classes, you can go back to your class. We will clear out of this room in a couple minutes and